Hello. In this video, we are going to discuss structure-activity relationships that affect the basicity of amines. Amines are a class of compound which involve nitrogen being singly bound to three groups, R1, R2, and R3, any of which or all of which might be hydrogen. The key feature is that these groups are singly bound to nitrogen, and nitrogen is left with a lone pair. This lone pair on nitrogen can accept the donation of a proton, which makes the amine a base. And it's the tendency for amines to act as a base that is what we're going to talk about in this particular video. When it picks up a proton, H+, it forms an ion that has a +1 charge, in which the lone pair on nitrogen has now been converted into a nitrogen-hydrogen single bond. Since both of the electrons came from the nitrogen, we call this a coordinate covalent bond, but once the hydrogen has bound to the amine, each of these four bonds is indistinguishable, except to the extent that R1, R2, and R3 are distinguishable from each other. We classify amines by how many of the R groups, R1, R2, and or 3, are hydrogens and how many are some kind of alkyl group. So, if, for example, if all three R1, R2, and R3 are hydrogens, then we simply call this the important compound ammonia. And then when it reacts with hydrogen, we get an ammonium ion, which is very, very common in inorganic chemistry. If one of the R groups is an alkyl group, then we call this a primary amine. If two of the R groups are alkyl groups or some other kind of group that's not a hydrogen, then we call this a secondary amine. And if all three of the R groups are not hydrogens, then we call it a tertiary amine. And the number of non-hydrogen groups and the type of group that they are will very greatly affect the basicity of the amine. Our standard for comparison for the basicity of amines is the case where R1, R2, and R3 are each hydrogen, so that we have ammonia. And we know that ammonia is a weak base, being that if it reacts with hydrogen, the equilibrium will not be completely on the right-hand side. And in fact, the equilibrium constant is somewhere around 1.8 times 10 to the minus 5. So to be extra clear, we make sure that we write this with double arrows to show that there's an equilibrium involved. When we're talking about acidity or basicity, we're talking about equilibrium. So we're talking about the relative proportions of the product and the reactants once we've reached equilibrium. The more tendency there is to form product, the stronger we say that the base is, the less likely it is to form this particular product, the weaker of a base that we say the amine is. So this video is going to look at which particular factors in the structure of the amine will lead it to be either a stronger or a weaker base. So in the first half of the video, we are going to look at the effects of electron withdrawing groups. And in general, the electron withdrawing groups are going to be the very electronegative elements, and important members of that class are the halogens. So we're going to look at the series of the base compound ammonia, and then if we replace one of the hydrogens with fluorine, two with fluorine, and then if we replace all three with fluorine, can we predict the effect on the basicity of the compound? So again, this is ammonia. This is often called fluoramine. This compound is difluoramine. And then the third compound could be trifluoramine, but is also often called nitrogen trifluoride. Please see the following figures to see computed structures of these four compounds. A key structural feature in the basicity of an amine is the availability of this lone pair to form the coordinating covalent bond with a proton. Anything which makes this proton lone pair more available to the proton makes it a stronger base. Anything that makes it less available will make it a weaker base. So we know that the effect of electron withdrawing groups is to withdraw electron density from the neighboring atom. So that means this lowers the electron density in the lone pair, which makes it less available to donate. Therefore, the electron withdrawing group makes this a weaker base. So going from ammonia to fluoramine, we would predict that fluoramine is going to be a weaker base. Now if we have two fluorine atoms, the effect is even greater. We have even more electron density being drawn away from the lone pair towards the fluorine atoms, which are extremely electronegative, the most electronegative of all the elements. So this species is even weaker than this one. And then if we have three fluorine atoms, three very, very electronegative elements, all pulling electron density onto themselves, less electron density is available in the lone pair on the nitrogen. So we would predict, and calculations confirm this, that this is by far the weakest of the bases of this pair. If we were asked to put these compounds in order of basicity, the strongest base would be the ammonia. The next would be the fluoramine, which is greater a strength of base than the difluoramine. And the least strong base, the weakest base of all in this series, would be the nitrogen trifluoride. Now suppose that we perform the same thought experiment, but now instead of using fluorine, we are going to replace with chlorine. We know that chlorine is a very electronegative element. It's tied for third with nitrogen after fluorine and oxygen. So we know it's very electronegative, but not quite as electronegative as fluorine is. So again, our basic principle is that whatever makes the electron density here greater on the nitrogen will make it more available, will make it a stronger base, whereas things that withdraw electron density will make it a weaker base. So we see this compound here we call chloramine. These kind of compounds form from the reaction of disinfectants, particularly in pools, these kind of things develop. So if you have one chlorine, chlorine is going to withdraw electron density. So chloramine is going to be a weaker base than ammonia. Again, the effect of electron withdrawing groups is cumulative. So if we have two chlorines, the effect is greater than for one chlorine. So dichloramine is going to be an even weaker base than chloramine is. And then finally, our last compound here is nitrogen trichloride. We have three electron withdrawing groups. So we imagine that this is going to be the weakest base of all. Please see the following figures to see the computed structures of these three chloramines. So again, based on our understanding of electron withdrawing groups, we can put these again in order, and we realize again that ammonia is the strongest base, chloramine is the second, dichloramine is the third, and nitrogen trichloride is the weakest base of this entire series. What about the next halogen, bromine? So we can again perform our thought experiment and replace hydrogen sequentially by the halogen bromine. So the first compound here is bromoamine, then we have dibromoamine, and then lastly we have nitrogen tribromide. Please see the following figures for computed structures for these three compounds. So again, we want to be able to predict the order of the basicity of these compounds. Now, what you might realize is that bromine, while electronegative, is actually less electronegative than nitrogen. So if we compare the substituents to nitrogen, fluorine was more electronegative, chlorine was equally electronegative, and bromine is less electronegative than the central nitrogen. But that's not our point of comparison. We're comparing the substituent to the electronegativity of hydrogen. So fluorine, chlorine, and bromine are all more electronegative than hydrogen. So this is our comparison compound. So we have to compare our substituents to hydrogen, and bromine, while not as electronegative as fluorine and chlorine, is still more electronegative than hydrogen. So we predict that having one bromine here should withdraw electron density from the nitrogen, at least relative to what the hydrogen did. So the lone pair is less available to form a coordinate covalent bond. So we predict that this is going to be a weaker base. So it's less strong of a base than ammonia. Having two bromines makes the effect even bigger, so we even have more withdrawal of electron density. So that's going to be a weaker base. And then three bromines would give us the weakest base of all in that series. And we'll see in a following table that when we compute the basicity of the amines in the gas phase, that the orders that we predicted are confirmed by calculations. Can we use the fact that we know or can look up the order of the electronegativities of the halogens? So let's compare the monosubstituted compounds where we replaced hydrogen with either one bromine, one chlorine, or one fluorine with the reference compound of ammonia. Well, we know that bromine is more electronegative than hydrogen. So we predict that bromine is going to withdraw more electron density from the nitrogen than hydrogen did, thereby making this compound a weaker base than ammonia. And this is confirmed by calculation. We also know that chlorine is more electronegative than bromine, so we predict that it's going to withdraw more electron density from the lone pair, and thereby make this compound a weaker base than the brominated compound, and this is confirmed by experiment and by calculations. Last but not least, we know that fluorine is the most electronegative of all the elements, so it's more electronegative than chlorine. So we would predict that fluorine atom is going to withdraw more density from the nitrogen lone pair than chlorine would, thereby making this compound the weakest base in this particular series. And that again is confirmed by experiment. So please see the following table, which lists the proton affinities in the gas phase. So in the table, the larger the negative value, the stronger the base. The smaller the magnitude of the negative number, which is also would be larger, but the smaller the magnitude of the negative number, would be a weaker base. So in table 1, the strongest base, for your reference, is ammonia, which is listed in the first line. So relative to that, all the other substituted amines are weaker bases, and they have a smaller negative value for the proton affinity in the gas phase. For our first two sets of comparisons, we looked at first the number of halogens that were added, and we saw that 3 had a bigger effect than 2, which had a bigger effect than 1, which had a bigger effect than no halogens. So we were always able to put things strictly in order based on the number of the halogen atoms that were there, so long as we were comparing the same halogen. We saw that if we were comparing different halogens, that fluorine had the biggest effect, followed by chlorine, followed by bromine, relative to ammonia. But we were not able to obviously pick up a priori based upon our assumptions is how different numbers of different halogens compare to each other. So this is one area where electronic structure calculations can answer the question for us. And interestingly enough, which you'll be able to see in the following table, is that if I have 3 bromine atoms, it's not a surprise that this is a weaker base than ammonia. We've already figured that sort of thing out. What is surprising, though, is if I have only 2 chlorine atoms, the effect of 2 chlorine atoms is actually more electron withdrawing than 3 bromines. And that's not by prediction, we're only getting that by the results of calculation and an experiment. Similarly, if I compare just 1 fluorine atom, fluorine, it turns out, although we might not necessarily have predicted this, that 1 fluorine atom is so electronegative that it has a greater electron withdrawing effect, at least in this series of amine compounds, than 2 chlorines. So in the following table, table number 2, the various amines are all sorted in order of their proton affinities. So you'll see at the top of the table is the strongest base, which is ammonia in our comparison, and at the bottom of the table is the weakest base, which is the nitrogen trifluoro compound. And then you'll see in between how various numbers of the different halogens stack up to each other. We have not specifically looked at the case where we've already mixed the halogens in the same compound, and we're not going to look at that in this particular video. In the remainder of the video, we are going to look at the effect of electron releasing groups to see the effect of electron releasing groups on the basicity of amines. And again, we're going to compare the basicity with the basicity of ammonia as our parent compound. So now let's imagine that we take one of the hydrogen groups and replace it by an alkyl group. So in the first case, we replace it by a methyl group, and this gives a compound called methylamine. If we replace it by an ethyl group, this gives us ethylamine. If we replace it by a propyl group, so this is 1-propylamine or N-propylamine, and not shown here, but we'll see a figure for it, we've also computed the structure of N-butylamine or 1-butylamine, where this R group is now a butyl group. Please see those computed structures in the following figures. since we replace one of the hydrogens by an alkyl group, we see that this particular series is a series of primary amines. So we want to see the effect of increasingly longer alkyl chains in a primary amine, how it affects the basicity. Well, we recall that from our general knowledge of substituents, that alkyl groups are mildly electron releasing. So they tend to push electron density onto the neighboring atom. So we would predict that these would push electron density onto the nitrogen and thereby make the lone pair more available for bonding. Another equivalent way of thinking about the same thing is the presence of these electrons in the electron releasing group increases the electron-electron repulsion with the electrons in the lone pair and thereby raises the energy of the lone pair. When you compute the energy of lone pairs, the higher the energy of the lone pair in a related compound, the more available the electrons are, the more willing they are to share, the stronger the base. So the higher the energy of the lone pair, the stronger the base. So we predict that by adding a methyl group instead of a hydrogen, that we would make a stronger base in this case. And it turns out that it's absolutely true. It's confirmed by both experiment and by calculations. If we have an ethyl group, the ethyl group has even more electrons here, so it's going to have an even greater effect releasing electrons onto nitrogen and making the nitrogen lone pair more available for bonding will make it a stronger base. A propyl group has still more electrons, so we would predict that methylamine is going to be a stronger base than ammonia. We would predict that the ethylamine would be even stronger base than methylamine, that propylamine will be a stronger base than ethylamine, and then even though it's not shown on the board here for the sake of clarity, but we've computed for the 1-butylamine, since a butyl group is even longer and has more electrons than a propyl group, the N-butylamine would be an even stronger base than the propylamine. Now, one thing to point out here is that while we talk about electron withdrawing and electron releasing groups, in general practice, the effect of electron withdrawing groups is generally far more dramatic than the effect of electron releasing groups. And a close comparison of the tables that you'll see in the video show that this is true. Adding more and more alkyl group, a longer and longer alkyl group to it, makes a stronger base than ammonia, but looking at the magnitude of the proton affinity, it doesn't change by anywhere near the same amount as the effect of adding just one electronegative element would have in weakening the basicity. So it turns out that, at least from what we know so far, it's a lot easier to weaken the basicity than it is to increase the basicity relative to ammonia. For the final analysis in this video, we want to look at the effect of replacing not just one hydrogen with longer and longer alkyl chains. We want to look at replacing each of the hydrogens with the same alkyl group, but repeatedly, as we did with the halogens. So in the first case, we have hydrogen replaced with a methyl group, so we have methylamine, which we've seen before. This is a primary amine. We're going to replace a second hydrogen with a methyl group, and we get dimethylamine, which is a secondary amine. And then if we replace the last hydrogen with a methyl group, we have trimethylamine. Please see the following figures which show computer structures for these compounds. we are showing this series because it actually gives a surprising result. Most of the results we've looked at so far are exactly in line with our chemical intuition. So we've already seen that methylamine is a stronger base than ammonia, and we understand that in terms of the electron releasing effect of the methyl group, making the lone pair on nitrogen higher in energy and therefore more available to share, making this a stronger base. In line with what we saw from the halogens, where 2 is better than 1, if we have 2 methyl groups, we know that this methyl group releases more electrons than the hydrogen it replaced, so we would imagine, and we'd be correct, that 2 methyl groups have a greater electron releasing effect than simply 1 methyl group and a hydrogen would. Therefore, that dimethylamine would be a stronger base than methylamine, which is stronger than ammonia. So far, so good. The problem becomes when we have 3 methyl groups. Now, if we compute the basicity of this in the gas phase, we get exactly what we would predict intuitively, that 3 has a greater effect than 2, has a greater effect than 1, has a greater effect than 0. So we get that this is the strongest base in the gas phase, trimethylamine, followed by diethylamine, followed by methylamine, followed by ammonia. But in actual solution, in aqueous solution, this is not true. Surprisingly, this is a far weaker base than ammonia is in aqueous solution. And we'll try to show why that is so. The problem is that the presence of the 3 methyl groups makes the approach and the binding of hydrogen, especially H plus being donated from the solvent, more difficult. So it's a steric hindrance problem. So that even though electronically the effect of the 3 electron releasing groups should be to make this a stronger base, their presence by hindering the approach of not even just the hydrogen, but the hydrogen is going to be bound to neighboring solvent molecules. So because of the effect of interacting with solvent, this ends up being surprisingly a weaker base than any of the other ones in the series. So we'll see that when we compute the effect in the gas phase, it's exactly what we would predict, but when we compare it to experiment, it contradicts completely, and this is a sign where the effect of solvent more than overwhelms the effect of electronic factors. So also please see that we'll have a following figure which shows the relationship between the computed proton affinities in the gas phase and the basicity of the substituted amines, omitting this one case. So you'll see that if we omit this one particular case, there's actually a very strong correlation between the electronic effect in the gas phase and the actual basicity constant Kb in aqueous solution. To keep that graph looking good, we've omitted this one, which would be wildly off the graph. So it shows that so long as we have primary or secondary amines, we can predict their basicity simply by the electronic effect in the gas phase. But once we get to tertiary amines, the effects of steric hindrance and the solvent become sufficiently large that our predictions from a gas phase result are not accurate. So please take a look at the following table and the figure, which again is showing the correlation between the computed proton affinity in the gas phase and the Kb in aqueous solution, which leaves off this particular compound, trimethylamine. As always, I thank you very much for your attention. Have a good one.